So we want to talk about the difference between permutations and combinations. So when we talk about a permutation is an ordered list of items, whereas a combination is an unordered list. So it's not really a list at all, it's a set. So in a list, we're going to have a first thing, a second thing, a third thing, and a fourth thing. As we learned about when we were talking about sets in our previous sections, sets are unordered. So the order we put things in a set is not important. So the set ABC is the same as the set CBA, is the same as the set BAC, and so forth. So the difference is, when order matters, we're going to use a permutation. When the order doesn't matter, we're going to use a combination. So let's take a look at example 1. Fran, Cloud, Sid, and Tara are getting their photograph taken. How many photographs would be needed to show all the ways that they can stand in a line together? So we have 4 people, and we want to know, well, how many different arrangements do we have of these 4 people? So, for instance, if I did Fran, Cloud, Sid, and Tara, if I change the order, Tara, Sid, Cloud, and Fran, that would be a different line, right? So that would be a different picture. So thinking back to what we did in 7.3, we have 4 people that we need to arrange in a line. So we're going to have 4 stages. And how many choices would we have for the first person in line? Well, how many people are there? 4. So then how many choices would we have left for our second stage? 3, then 2, then 1. So that would give us 4 times 3 times 2 times 1. So there would be 24 photographs needed to get all possible ways that we could rearrange 4 people in a line. All right, so this type of counting, as we saw last time when we were doing passwords and a whole bunch of things, leads to us having to multiply all of the positive whole numbers together all the way down to 1. So it happens so often that we're actually going to define it as a function. So its name is the factorial function. So n factorial, written as an n with an exclamation point after it, is defined by the relationship n factorial is equal to n times n minus 1 factorial for n greater than 0, and it's equal to 1 when n equals 0. So the last line really says this: we define 0 factorial to be 1. So when we say, for instance, 5 factorial, it's telling us that 5 factorial is the same as 5 times 4 factorial. Because it says n factorial is equal to n times n minus 1 factorial. But then 4 factorial would be the same as 4 times 3 factorial. And 3 factorial would be the same as 5 times 4 times, well, 3 times 2 factorial. And it all chains together to 5 factorial at the end of the day is just 5 times 4 times 3 times 2 times 1, which is what we would expect. But we'll see these partial expansions will have uses, and we will use them sometimes to simplify certain things. All right, so for example 2, we wish to simplify the following. So 4 factorial by definition is just going to be 4 times 3 times 2 times 1, which is 24. That's the same as we got in example 1. That's how many ways we could rearrange 4 people in a line, is 4 factorial. Let's take a look at our next one. So here we're going to use a partial expansion. So we want to simplify 7 factorial over 3 factorial. So if we write them out the long way, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah. We are. We're just writing it all out. And then we have our 3 factorial. And I'm going to pair it up down here, 3 times 2 times 1. And we'll notice here, all of those factors are the same, so they reduce out. So then we're left with 7 times 6 times 5 times 4. So 7 times 6 is 42. 5 times 4 is 20. So that gives us 840. So 7 factorial divided by 3 factorial is 840. So we could note that since we're going to get down to 3 factorial, and we noticed all of these things are the same, we could have just done 7 times 6 times 5 times 4 times 3 factorial over 3 factorial, and then those are the same and they cancel out. So this is what I was talking about earlier, where these partial expansions may be helpful depending on what we're trying to simplify. Because we only counted our 7 factorial down to 3 factorial, so 7 times 6 times 5 times 4 times 3 factorial, because we had a 3 factorial in the denominator. So at that point, we could just reduce them out, and we were done. So building on that idea, we'll notice in our denominator here, we have a 5 factorial. So we could do our 7 factorial would be 7 times 6 times 5 factorial over 2 times 1 times our 5 factorial. So then here, our 5 factorials reduce out, and we get 6 times 7 is 42 over 2, which is 21. So in simplifying some more complicated type factorials, that partial expansion will save us a lot of brute force work. But it turns out that we can also use our calculator to help us out with some of these. So on our calculator, we can find our factorial button by going to our math menu, and then we have to go all over to PRB, which stands for probability, and we go down and we'll see that it is choice number 4. So for instance then, if I went alpha y equals, and I said 7 math, and then I come over to factorial, all over 2 factorial, over 5 factorial, press enter, our calculator agrees with our by hand reduction that 7 factorial over 2 factorial times 5 factorial is going to be 21. So once again, our factorial on our TI calculator is found under probability. You can also find factorials in Excel by typing factorial. Don't try to just type the exclamation point. It doesn't work. So, all right. With that said, let's take a look at our next example. We have Fran, Cloud, Sid, and Tara are joined by Paulum, Porum, and Rosa in getting their photograph taken. So that the photographs match the previous ones, they are only going to have 4 people in each photograph. how many photographs would be needed to show all of the ways that they could stand together in a line? So once again, we're going to be rearranging them into lines of 4 people. But this time, how many people do we have to choose from for the first slot? Well, let's see. We have our original 4 plus 3 more. So how many choices do we have total?
7.
7. So we have 7, then 6 times 5 times 4. And that's how many we're going to get. So if we do this on our, we multiply it together, 7 times 6 times 5 times 4, we get 840. We're like, hey, wait a minute. I'm pretty sure we got that number before. That was 7 factorial over 3 factorial, right? Because we picked our group of 4 people out of 7, so that would be 7 factorial, but then we weren't picking those last 3 people, so we would divide by that, and we get this. We'll talk more about what I'm actually doing there in a second, because there is a name for that, but we do want to notice that we get the same thing when we do this. So, speaking of which, let's take a look at what exactly happened there. And we're going to now formally define what it is to be a permutation. So a permutation of n items taken r at a time is an ordered list of r items chosen from a set of n items. The number of permutations of n times taken r at a time is given by, and we're going to define a new symbol for permutations, p of nr, where n is the number of items in the big set, and r is the size of the subset that we're selecting. We'll notice that our formula is n times n minus 1 times n minus 2 all the way down to where we stop. Well, that's exactly what we did right here. That's this part. Or we can realize that same formula by doing n factorial over n minus r factorial. So anytime we need to arrange n items in subsets of size r, where the order matters, we can use this formula. So as we said in the previous example, p of 7, 4 is 7 factorial over 7 minus 4 factorial, which would be 7 factorial over 3 factorial, which was what we wanted. So a couple of things I do want to mention. Permutations of this form happen quite often. So instead of having to type it in using the factorial notation, on our calculator, we'll notice this choice right here, just above where we have the factorial, is the notation that our calculator is going to use for permutations. So this guy right here is our permutations. That's P of nr as defined above. The way we put it into our calculator then is we're going to have to put the number n into our calculator first, then come select this function, and then put r in. So let me illustrate. So the way we would type this into our calculator, if we wanted to calculate p of 7, 4, you put the 7 in first. You then go to your math menu, over to our probability, and we select it. So we have 7 NPR, and then we choose 4. We press enter. That's not the right number. That's 7 factorial is 840. because you have a color version, so it's going to be different. Very strange. So we get 7 permute 4 gives us 840, which is the same number we calculated above by doing the multiplication. So when putting it in our calculator, our format is we type the n, then we select NPR, and then we select the R. And then that will calculate it directly instead of us having to put the factorial in, which will save us a little bit of time when we have to do that. All right. So now, let's take a look at our next example. And we want to compare this with our very first example. So this time, Fran, Cloud, Sid, and Tara need to form a committee with 4 members. How many committees could they make? Well, how many of them are there? 4. And they need how many people on the committee? 4. So how many committees could they make out of 4 people? 1. So we're only going to have one possible committee. And what is that? It's going to be Fran, Cloud, Sid, and Tara. Well, why is there only one committee? Well, what if I changed the order? What if I did Tara, Fran, Cloud, and Sid? Is that a different committee than the first one?
Same people.
Same people. So in this case, does the order matter? No. So here, when forming a committee, we have an unordered set. So even though there were 24 ways we could have arranged them into a line, there's only one committee because it's the same 4 people in the line the whole time, right? So that's the essential difference between a permutation and a combination. Permutations, the order that the list is in matters. Combinations, like this, the set of people is the same regardless of which order I write them down in. And since we're forming a committee, we only have one possible committee from those 4 people. All right, so let's keep building on this. So now let's ask ourselves a harder question. So just to help us kind of visualize what's happening, in our next example, I went ahead and listed all possible groupings. So let's read our question, and then we're going to do some color coding to help us visualize what's happening. So it says, Fran, Cloud, Sid, and Tara need to form a committee with 3 members. How many possible committees can they make? So this one's different. So now we have 4 people to choose from, and we need a committee with 3 people. So we listed all of the permutations of 3 people. So remember, the permutations for 3 people is going to be what? So it's going to be 4p3. So if we calculate 4p3, we get 24. So I've listed all 24 possible permutations of that set. But as we saw in the previous example, in example 4, even though we had 24 or whatever it was possible permutations, there was only one committee with 4 members, right? So we need to find all of our committees that are going to be the same in this. So we have 24, but this is an overcount. So how much did we overcount by? Well, let's find all of the committees, so the permutations that contain Fran, Cloud, and Sid. So I have a Fran, Cloud, and Sid. Fran, Sid, Cloud. Okay, that's the same. Fran, Sid, Tara. Nope. Fran, Tara, Cloud. Nope. Fran, Tara, Sid. Nope. Cloud, Fran, Sid. Okay. Cloud, Fran, Tara. No. Cloud, Sid, Fran. That's a yes. Cloud, Sid, Tara. No. Cloud, Tara, Fran. Nope. Cloud, Tara, Sid. Nope. Sid, Fran, Cloud. Okay. It's the same three people. Sid, Fran, Tara. Sid, Cloud, Fran. Okay. Sid, Cloud, Tara. Sid, Tara, Fran. Sid, Tara, Cloud. No. Tara, Fran, Cloud. No. Tara, Fran, Sid. No. Tara, Cloud, Fran. No. Tara, Cloud, Sid. No. Tara, Sid, Fran. No. And Tara, Sid, Cloud. No. All right, so we had 6 of them that we found that contained Fran, Cloud, and Sid. All right, let's go to our next one. So our next one is Fran, Cloud, and Tara. So Fran, Cloud, Tara. Fran, Tara, Cloud. Fran, Tara, Sid. Fran, Cloud, Tara. Cloud, Sid, Tara. Nope. Cloud, Tara, Fran. That's a yes. Cloud, Tara, Sid. No. Sid, Fran, Tara. That's a yes. And then Sid, Cloud, Tara. That's a no. Sid, Tara, Fran. Nope. Sid, Tara, Cloud. Nope. Tara,
Professor,
Fran. Yes?
you highlighted Sid, Fran, Tara when it's supposed to be Cloud, Fran, Tara.
Oh, thank you. And Sid, Cloud. Yeah, it's Cloud, Fran, Tara. Okay. Cloud, Fran. Okay, good. Thank you. Sid, Cloud, Tara. Sid, Tara, Fran. Nope. Sid, Tara, Cloud. Nope. Tara, Fran, Cloud. Yes. Tara, Fran, Sid. Nope. Tara, Cloud, Fran. That's a yes. Tara, Sid, Cloud. That's a no. Tara, Sid, Fran, no. And Tara, Sid, Cloud. So once again, thank you for helping me. How many things did we end up highlighting? 6. All right, let's keep going. If we go a Fran, Sid, and a Tara, we have a Fran, Tara, Sid. Cloud, Sid, Tara. So that's a no. Cloud, Tara, Sid, no. Sid, Fran, Tara, that's a yes. Sid, Cloud, Tara, no. Sid, Tara, Fran, that's a yes. Sid, Tara, Cloud is no. Tara, Fran, and Sid, that's a yes. Tara, Cloud, and Sid is a no. Tara, Sid, and Fran is yes. And Tara, Sid, Cloud is no. Once again, in blue, 1, 2, 3, 4, 5, 6. All right, let's pick up our last one. So we have a Cloud, Tara, Sid. A Cloud, Sid, Tara. A Sid, Cloud, Tara. Sid, Tara, Cloud. And a Tara, Cloud, Sid. And a Tara, Sid, Cloud. So in each of those groups, we ended up with 6 things. Why is that? Well, let's see. We had 24 possible ordered pairs that contained what size of things? 3. How many ways can we arrange a set of size 3? 3 times 2 times 1. Oh, 6. Oh, that's why all of the colored subsets were size 6, because we were rearranging groups of 3 things. So how many ways can you do that? 3 times 2 times 1. So that means we were counting all of those groups of 6, or these groups of 3, we were overcounting them 6 times. So this was the size of each group that was overcounted. So then to fix our 24 as an overcount, well, how many committees could we make? Well, how many colors did we have? 4, which is 24 divided by 6 gives us 4. Not with a factorial. Gives us 4. So this leads us to the following conclusion, which is a combination. So when rearranging n objects r at a time, where the order doesn't matter, we call that a combination. Combinations are given the symbol C. So C of nr is given by the n factorial divided by n minus r factorial. So we'll notice that we have this part, which we've seen before, and what is that? This is the number of permutations. And then we have this r factorial, and that r factorial is just what we saw up here. That was our overcount, right? The size of the groups that we were overcounting by, because order didn't matter. So here, our overcount was 3 factorial, which is 6, which gave us our total number of things. So we're just going to include that in our formula. So this is, we're dividing out the overcounts. And that gives us our formula. So this symbol is read as n choose r, and it can also be written in the form that looks like this, kind of like a big fraction without a fraction bar, and that is called, when it's written in that form, the binomial coefficient. And our formula is this: n factorial divided by r factorial times n minus r factorial. So this symbol is also in our calculator using the C. So if we go over to our probability menu in our calculator, we'll have that this is our combinations. And just like with the permutations, if we were to do example number our previous, we would do 4 choose 3. And when we do 4 choose 3, we get 4, which was the same thing that we were able to deduce by counting all of our rearrangements that were overcounts. So that guy is the same as either 4 choose 3, which is the same as 4 choose 3 on our calculator, and we get this. All right, so once again, we don't have to do all the factorials manually. Both the permutations and combinations can be found using their respective functions and formulas. All right, so let's go ahead and do a couple of these. And then we'll verify them using our calculator. So C 7.5 would be 7 factorial over 5 factorial times 7 minus 5 factorial. So that's 7 factorial over 5 factorial times 2 factorial, which would be 7 times 6 times 5 factorial over 5 factorial times 2 times 1. 5 factorials reduce out, 2 goes into 6 3 times, and we would get 21. Checking on our calculator, if we did 7 choose 5, we get 21. Okay.
I have a question.
Yes, sir.
What did you do?
All right, so let's go ahead and calculate 7 choose 2. So we go ahead and we have 7 factorial over 2 factorial times 7 minus 2 factorial. So that gives us 7 factorial over 2 factorial times 5 factorial. Well, wait a minute. These two things are the same. The only difference is in the denominator I have 2 factorial times 5 factorial instead of 5 factorial times 2 factorial. But they're going to give us the same thing because the order we multiply in doesn't matter. So this would really be, once again, 7 times 6 times 5 factorial over 2 times 1 times 5 factorial. Those reduce out, and we get 21 again. So interesting. 7 choose 5 is the same as 7 choose 2. Why would that be the case? Well, So we have our 7 things, and in the first one we're asked, well, how many ways can we pick a subset of 5, right? That would be these. And in the second one we're asked, well, how many ways can we pick subsets of size 2? Well, why would those yield the same values? Well, 7 choose 2. If I'm picking a subset of size 2, I'm not picking 7 minus 2. And in the green, what would I be picking? Well, I would be, that is not the color I want. There we go. In the green, I would be not picking seven minus 5, which is 2, and here it would be 5. So they're really just the negations of each other, right? So that's why we get this symmetry, because 7 choose 5 has to be the same as 7 choose 2, because I'm either rearranging the first 5 or the last 2, but I'm going to get the same idea of things that are left over. So they must be equal. And so play around with it a little bit if you don't believe me, but that will always be the case. All right, so speaking of rearranging things, let's take a look at example number 7. So Powerball. So, in case you've never played the Powerball Lottery, which we do have in Arizona, well, they have it in a lot of states, but Arizona participates. The Powerball Lottery is played by choosing 5 numbers from 1 to 69 for the white balls, and then selecting a number from 1 to 26 for the red Powerball. It costs $2 to play. Use this to answer the following question. Okay, how many different Powerball tickets are possible? So, well, you have to pick how many numbers out of 69? 5, right? Does the order that you pick the numbers in Powerball matter? No, because when they draw them out of that thing, they just put them in numerical order when they're done, so it's easier for you to identify. But you don't have to match the order that the balls are picked in, right? There's no data for that. So we're going to actually have how many stages in this experiment? Well, we're going to choose our 5 white balls, and then our next stage, does the red ball have any effect on the white balls? No, because they're going to be independent from each other. So we've decided that for stage 1, we're going to pick five white balls, and then stage 2, we're going to pick, well, we're not going to, and then for stage 2, we're going to pick 1 red ball. So how many ways can we select 5 balls from 69 balls if the order doesn't matter? So combination or permutation? It's a combination because the order doesn't matter. And as we discovered, if we want to take subsets of size 5, that's going to be our R, and our N is going to be how many ways or how many balls we have total. So we're going to have for our stage 1, we're going to have 69 choose 5. So there's 69 choose 5 ways to select 5 numbers out of 69. And then how many ways can we pick a red ball? Yeah, so how many choices are we going to have for picking that number? So I'm actually getting us off on something else. So, all right, we're going to have 26 possible choices for our Powerball. So before we do this, let's analyze a little bit more. So we're looking at it this way. Let's enumerate our things. How many choices do we have for our first number? 69. And how many choices do we have for our second number? Well, 68, because we've already picked one. How many choices do we have for our next number? 67. How many choices do we have for our next number? 66. And how many choices do we have for our 65? Okay. And then for our number in red, how many choices do we have? 26. Okay. So then, if my stage 1 is this and my stage 2 is this, how many Powerball tickets are going to be possible? So 69 times 68 times 67 times 66 times 65. So that's my stage 1 times the number of Powerball choices is this. So I get 1,348,000,000 So 1,348,621,560. Stage 2, I have 26 choices, and when I multiply them together, I get this number. And my calculator is running out of display space, so what did it do? Yeah, it changed it to scientific notation. So that tells me there's going to be 10 zeros afterwards. So 10 zeros trailing a 3. So how many possible lottery tickets are there going to be? Well, let's see. 9 zeros is a billion. So 10 zeros is going to tell us that this is like 35 billion possible lottery tickets. So then for part B, how much would it cost you to buy every possible Powerball ticket? Well, there's 35 and some change billion at $2 a piece. It would cost you around $70 billion to buy every possible Powerball ticket. Well, that would explain why it is not a good idea to try to buy all the lottery tickets. Okay, so what do we think? Is this a good analysis or a bad analysis? So what did we do in stage 1? Did we do that right? So when we did 69 times 68 times 67 times 66 times 65, what was it we're counting? All right, so I want everyone to think on this for just a second and decide, did we do this right? Because this is the hardest part about counting. What did we just do? And did we actually count what we think we're counting? So think about it for a second. And, okay, so we wanted a combination, not a permutation. So this is not correct. So 69 choose 64. If we grab our calculator, what's that going to give us? It's going to give us a very different number. 69 math choose, not permute, 64 gives us, okay, we end up with 11,238,513. So that's our stage 1. What about stage 2? Well, it only had one thing in it, so stage 2 is correct still. So we had 29 choices because there's only one thing, so stage 2 is good. So then the total number of Powerball tickets, the correct total, the product of these two things, so times 29.
It's supposed to be 26.
26. Oh, thank you. Gives us this number. So, what's the moral of this story that we just went through? It's not always so easy to tell whether or not we're using combinations or permutations, right? So we have to be really, really careful and decide, does the order matter? So that gives us our number of tickets. So then to buy all of them, we times that by 2, which would give us our cost for buying every Powerball ticket. It's a lot smaller than it was. So the cost to purchase every Powerball ticket is this number, and let's add some commas to help us see what it is. So, not nearly as bad as when we erroneously used permutations, but still pretty expensive. So, to buy every possible Powerball ticket, what would we need? Almost, well, $584 million, right? So, the biggest Powerball, I think, broke $1 billion by a little bit. So, at that point, it may be a good idea, maybe, but then you would have to worry about splitting the prize or something else. Not to mention, I don't think it would be physically possible to try to buy almost 300 million Powerball tickets in 2 days. That would be a lot of tickets. You'd need an army of people filling things out to get that done. So that's why they have so many numbers in the lottery. Well, at least one of the reasons, so you can't game the system. All right, so let's move on to our next example and see if we can figure out what we're talking about this time. So we got to be very, very careful once again. And we want to talk about marbles this time. So a bag contains 3 red, 3 blue, 3 green, and 2 yellow marbles. How many sets of 4 marbles are possible? Okay. So before we do this problem, I want everyone to think for a second. How are we going to count this? Is there going to be multiple stages? What's going to happen? So we need to be able to come up with a plan. So we want to know, how many sets of 4 marbles can I make if I have a bag that contains 3 red, 3 blue, 3 green, and 2 yellow? So we are going to assume that each colored marble is indistinguishable. So I cannot distinguish one red marble from another red marble, right? So, all right. How are we going to count this?
Did you add them all together?
Okay, when you say add them all together, and then do what? So we're trying to make a set of 4 marbles, right?
Yeah.
Okay. And how many ways can we pick 4 marbles from this set? So, well, first of all, we're going to use the addition principle just to get the total number of marbles, right? Because that's our total number of choices. So you're absolutely right. We're going to add all of our possible choices of marbles together. That tells us that we have 11 total marbles to choose from, right? Well, now what size subsets of marbles do we want to pick? We want to pick sets of 4. So now we have to ask ourselves, does the order matter? No, right? Because these are going to be unordered sets. If I have red, blue, green, red, that's going to be the same as red, red, green, blue, right? In the end, we just care about what we have present, how many of each, right? So this is going to be a combination So we're going to do 11, choose 4. So we calculate our combination of 11, choose 4. And we are going to get 330 sets of 4 marbles. Okay. Let's move on to part B. How many sets of 4 are there such that each one is a different color? So how are we going to count that? So we want to count the number of subsets of size 4 where we have 1 red, 1 blue, 1 green, and 1 yellow marble.
So my first thought was to divide the 330 by the 3 and the 3 and the 2.
Okay, well, let's keep thinking. So what are our possibilities? Well, what do we need to do? So in order for our set to have 1 of each color, what needs to be true? So we're picking 4 marbles, so how many stages are we going to have? 4, right? So in my first stage, what am I going to need to pick? Well, how many red do I want? 1. So in my first stage, I'm going to need to pick red. And in my second stage, I'm going to need to pick blue. In my third stage, I'm going to need to pick green. And in my last stage, I'm going to need to pick yellow. So how am I going to make that happen? Okay, so how many ways can I pick a red marble? Well, first of all, how many red marbles are there? There's 3 red marbles, and how many red marbles do I want to pick? 1. Okay, so then that means out of the 3 red marbles, how many of them do I need to pick? 1. For the blue, how many blue marbles do I have? 3, and how many of those do I want to pick? 1. And for the green marbles, I'm going to have to, there's 3 green, and I want to pick 1. And for the yellow, I only have 2, and how many do I want to pick? 1. So then 3 choose 1 is going to be 3. So I'm going to have 3 times 3 times 3 times my last one is going to be 2, because 2 choose 1 is 2. So 3 times 3 times 3 times 2 is going to give me, what is that, 927 times 2 is 54. We get 54. All right. So let's talk about our next one. How many sets of 4 marbles are there in which at least 2 marbles are red? Okay. So what does that mean?
So out of the 54 sets,
Well, not necessarily out of the 54 sets, because if we have a set of, our total number of sets are 330, right? So we want to have 2 red marbles. So that means there's going to be, and it says at least. So at least 2 red marbles means I could have 2 red marbles, or I could have 3 red marbles. So we have to be a little bit careful with the word at least 2 of the marbles are red. So if at least 2 of the marbles are red, that means I could have 2 red marbles, or I could have up to my maximum, there's only 3 red marbles, right? So then, how are we going to have to count each of those? So our 2 sets, as we mentioned, involve our set having 2 red marbles and our set having 3 red marbles. All right, so we have at least 2 red means there are 2 possible sets. We need to count. And those sets are exactly 2 red and exactly 3 red. Because there's only 3 red marbles, right? So when we have the word at least, we need to be careful and enumerate very carefully the sets that we're talking about. So the first thing we need to worry about then is the exactly 2 red. So then in my choice algorithm, we're picking 4 things. So what do I need? So stage 1, I'm going to need to pick 2 red. And then my next stage, stage 2, pick 2, and specifically they need to be not red, right? So this is for my exactly 2 red. So how many ways can I pick 2 red marbles? Well, how many red marbles were there? Well, 3. So this is going to be 3, choose 2. And then in stage 2, I need to pick 2 marbles that are not red. So how many not red marbles are there?
8.
8. And I need to pick 2 of them. So there's going to be 8, choose 2 ways to pick 2 not red marbles. So if I pick 2 red and 2 not red, that gives me a set with exactly 2 red. All right, so now we need to calculate 3 choose 2, which is going to be 3, times 8 choose 2, and that's going to give us 84. different ways gives us 84. But that's not all of the ways that we can pick at least 2 red marbles. So that was to pick exactly 2, but we now need to calculate, well, how can we pick exactly 3 red? Well, if that's the case, we only have 3 red marbles, so our stage 1 this time is we're going to pick 3 red, and our stage 2 is we're going to pick 1 not red. So this time we have to pick all of our red marbles, so that's 3 choose 3 times, now of our 8 not red marbles, we need to pick 1, so that's going to be 8 choose 1. So 3 choose 3 is going to be 1, 8 choose 1 is going to be 8, so there's going to be 8 ways that we can pick exactly 3. So at least 2 is exactly 2 plus exactly 3. So using the addition principle this time, to find the at least 2 red, we found the number of ways to get exactly 2 and the number of ways to get exactly 3, and then we add them up, and that will give us 84 plus 8, which is 92. So there are 92 possible ways to get at least 2 red marbles. Whew. All right. There's a couple more on here. Our last one D reads as follows. How many sets of 4 are there in which no marbles are red, but at least 1 is green? How are we going to set this one up? So we want the sets of 4 marbles that contain no red marbles, but they have at least 1 green. Well, we just did an example of at least 2 red. So how are we going to get that to work? So, but we want at least one green, right? Okay. So, how are we going to do at least 1 green? So, at least 1 green is going to be exactly 1 green plus exactly 2 plus exactly 3. Right? So the at least says we need exactly 1, exactly 2, or exactly 3. Okay. So now we need to do something similar to like we did before. So we're going to need to pick exactly 1 green And what's our other condition?
No marbles are right and at least one green.
Okay. So if we do our first alternative, so our first stage is we're going to pick green. So for exactly 1, and then stage 2 is we're going to pick not red. So in stage 1, we want to pick exactly 1 green marble. So how many green marbles did we have total?
3.
3. So how many ways can we pick 1 green marble? 3, choose 1. So now stage 2, we want to pick no red marbles. But it's actually more than that. Because what else are we not allowed to pick? Well, I think you're answering a different question. What else are we not allowed to pick? You just told me what we were allowed to pick. So what else are we not allowed to pick in our stage 2? Green and red. Because we've already selected all of the green marbles that we can have, which is 1. So in stage 2, we're selecting not red, but we're also doing not green because we did green in stage 1. So how many not red and not green marbles are there? So we go back up to our totals, and we had, so we need not red and not green, so that's 3 blue and 2 yellow. So our not green and not red is going to be 5. We have 5 to choose from, so 5C2, right? Because that is our not green and not red. And we're selecting, hold on, we're making sets of 4. So we've got to select 3, right? Sorry. I was making the wrong size set. We need to select 3 marbles because we're making sets of size 4. We selected 1 in stage 1, and we're selecting 3 in stage 2. All right, that's exactly 1 green. Let's go to exactly 2 green. So if we want to pick exactly 2 green, we're going to do 3 choose 2, and we're still going to have our not red, not green, which is going to be 5. But now, this time, we've already selected 2 marbles, so we're going to select 2 from that set. And lastly, we need to do 3 green. That's going to give us 3 choose 3, and then from our remaining 5 marbles, we would need to pick 1. All right. So then we can calculate each of these by multiplying these together. So we have 3 choose 1 times 5 choose 3 gives us 30 ways. So then 3 choose 2 times 5 choose 2 also gives us 30. And then 5 choose 1 times 3 choose 3 is going to give us 5. So then the total number of sets is going to be 30 plus 30 plus 5 gives us, there are 65 sets which contain no red marbles, but at least one green marble. So, a couple of things we really should mention here. There was a more efficient way of doing this. And what I mean by that is, we enumerated our set at least one green, said exactly one green, exactly two green, or exactly 3 green, right? Well, what is the complement of at least one green? So when we said at least one green, that was exactly one green, exactly 2 green, or exactly 3 green. So the complement of at least one green is no green. Because the only possibilities for green marbles were no green, 1 green, 2 green, or 3 green, because there's only 3 green marbles, right? So what would be the complement of 1, 2, or 3? Well, we've eliminated 1, 2, or 3, so the only thing that's left would be 0, or none, right? How can we use that to help us? What did we learn about complements and counting? So one of the things that we learned is that the number of things in A union the number of things in A complement has to equal the total number of things. Because you're either in the set or you're not, right? So then we can use this to help us calculate these things individually. Because by the addition principle, sets and their complements are always have a non-empty intersection, so they're disjoint. So then if I'm trying to find one thing, I can find the amount of the other by calculating the complement. So the number of things in the set A is equal to the total number of things minus the number of things in the complement. So if you can figure out the number of things in the complement, you can then calculate the number that you are looking for. So the complement of at least one green is 0 green. So how can we count how many sets with no green marbles? All right, so how many sets, how can we use this to help us? So how many sets contain no red marbles? That's what we were really trying to find, right? So no red marbles, but at least one green. So let's start with the no red. How many sets contain no red marbles? So we're going to be choosing 4 marbles from not red. So there's 3 red and 11 marbles. So there are 8 not red marbles, right? So we need to choose. So how many sets contain no red marbles? Well, that would be, of the 8 marbles, what are we going to choose? Well, how many marbles are we choosing from the not red? Well, we're making sets of 4 marbles. So if we go 8, choose 4, we get 70. So this is the number of sets of 4 marbles with no red. Okay, so then here's where we can use the complement. We want at least one of them to be green, right? Well, how many of those contain no green marbles? Well, how would we calculate that? So of these sets right here, how many of them contain no green marbles? So if we want to contain 0 green marbles. So how many marbles did we have if we have no red and no green? Well, there's 3 green. So of these, five choose, because there's 5 marbles in that set that aren't green, and we want to choose out of that set all the not green ones, right? So that would be 5 choose 4. Have no green marbles. So if that's the case, 5 choose 4 is 5. So if these have no green marbles, out of the 80, or out of the 70, then 70 minus 5 equals 65 is at least 1 green. Which is the same number we got up here. So basically we had sets of marbles, of 4 marbles with no red, and then we counted, well, how many of them have no greens? Well, 5. If only 5 of them have no green marbles, then the remaining 70 minus 5, which is 65, have to have at least 1 green, which is exactly what we did here. We used the complement of that set, because it was easier to count how many had 1 green or had no greens than it was to count how many had 1 green, 2 green, or 3 greens. That's what we did here directly. We counted how many had 1, how many had 2, how many had 3, and then multiplied it by the ways we could pick the other marbles. 2 ways to get the same answer. All right, so that was actually this next bit. So from the previous problem, how many sets of 4 are there in which no marbles are red, but at least one is green, can be calculated using the complement. All right, so this last bit is for you guys. All right, so let's talk about our first one. So how many possible sets of marbles would there be? Well, how many marbles do we have total? We have 5 plus 3 plus 4 gives us 12 for our total. And then how many marbles are we trying to select?
3.
So we want to select sets of 3. So then out of our 12 choices, we want to choose 3. So then 12 choose 3 is going to give us 220 sets of 3 marbles. Okay. So now for part 2, how many sets of 3 marbles include no red? Well, how many marbles do we have if we have no red? So no red is 3 plus 4, which is 7. And from this now, we want to select from those 7 marbles 3, right? So we're going to have 7 choose 12. Wow, I did that backwards. It's going to be 7 choose 3. And that's going to give us 35. So of those 220 possible 3 marble sets, there are 35 that contain no red marbles. All right, let's move on to our next. Couple. So next, how many sets of 3 marbles include at least 1 red? And how many sets of 3 marbles include 1 red, 1 blue, and 1 green? All right. So for 3, how many sets of 3 marbles include at least 1 red? Well, at least 1 red is going to be 1 red, exactly 2 red, exactly 3 red, exactly 4 red, or exactly 5 red, because there's 5 red marbles. So at least 1 would be 1 red, 2 red, 3 red, 4 red, or 5 red. But we're only picking 3, so we'd never make it to 5, but there are 5 red marbles. So then it would be exactly 1, exactly 2, or exactly 3 red. Well, that is the complement of the previous example. So this is the complement. And we know that the total is 220. So it's going to be 220 minus 35 gives us 185. So the long way would be exactly 1 red plus exactly 2 red plus exactly 3 red. And then if you calculated each of those individually and added them up, you're going to get our same number, 185. So oftentimes when we have at least statements, the complement can be helpful because it will save you a lot of work, because if the complement of the event is easy to count, we can find our answer indirectly. All right, 3 minutes and 1 question. I think we got this. How many sets of 3 marbles include 1 red, 1 blue, and 1 green? So we're picking our 3 marbles again. We have 5 red, 3 blue, and 4 green. So how many ways can we pick 1 red from 5? Well, that's going to be 5 choose 1. How many ways can we pick 1 blue from 3 blue? That's going to be 3 choose 1. And how many ways can we pick, what is it, 4 green? 4 green, 1 green from 4 is going to be 1. So that's going to be 5 times 3 times 4, which is going to give us 60. So there would be 60 sets of 3 marbles where 1 was red, 1 was blue, and 1 was green. All right.